Hi everyone, and welcome to our physics live stream. So what we're going to do tonight is we are going to go through the entirety of the first physics paper. This is obviously focused on OCR Gateway, but there could well be bits that come up on other exam boards if you're happening to do those. As usual, we'll go through everything for the combined, the triple science, higher and foundation, and I will try and point out where we're changing between those different bits so you know which bits are relevant to you. Right, let's make a start then. Let's kick it off with P1. Now, the good news is, if you did some learning for your chemistry, you already know the first bit of your physics. Because P1 starts off with the history of the atom, basically. So we start off with those four important scientists, Dalton, Thomson, Rutherford and Bohr. So Dalton was the first one, and he came up with the idea of these tiny indestructible spheres. So all atoms in the element are the same, but different elements have different atoms in them. Number two in our list of scientists is J.J. Thomson. So what Thomson did was he carried out these cathode ray experiments, and he discovered that those cathode rays were made from electrons. And he said these electrons are negative. So from that he came up with the idea of the plum pudding model. So this positive cloud with these little negative electrons dotted around in there. Scientist number three is Ernest Rutherford. Now Rutherford worked with Geiger and Marsden, and they carried out these experiments firing these alpha particles, which are positively charged particles, at these very thin sheets of gold foil. Now had the plum pudding model been correct, those would have gone straight through, but they didn't. Some bounced straight back, others bounced off at different angles. So from that he decided there must be this tiny positive nucleus surrounded by electrons. Scientist number four is Niels Bohr, and he was the one that suggested that electrons move in these fixed orbits called electron shells. So there are four scientists, exactly the same as we did in chemistry, so nice bit of overlap if you've already learnt them. One of the questions that does come up every so often as a multiple choice one marker is the size of the atom. So an atom is 1 times 10 to the minus 10 meters. So just look for that and you will be able to get it. Let's have a look, hold on.
Is that better on the echo? Let me know if that works a bit better. If we're talking about the radius of the nucleus, then that is 1 times 10 to the minus 15 meters. So we've got those two kind of key values there. Radius of the nucleus doesn't tend to come up, but the diameter of the atom, that does, okay? So 1 times 10 to the minus 10, that is what we're looking for the atom. May not be exact, but whatever is closest to that would be the correct answer there. Next up, we are going to come on to thinking about density. Now, remember, the joy of this year, the one thing that they've actually done that's really nice this year is they're giving you every single formula that could come up on this paper. So remember to use that formula sheet. Don't just ignore the bit of paper there with all of the great formulas on it. Turn it over and please use it. They've even ordered it based on the units. So the first formula on there is going to be density. So what we actually have then is density is how much mass there is in a certain volume, okay? So on your formula sheet you will find density is the mass divided by volume. You need to look out for the mass being given to you in grams, not kilograms, because standard units for mass are kilograms. So if in the question they've given you a mass in grams, divide by 1,000 to get it in kilograms first. So watch out for that little quirk they throw in on anything mass related. Anything in grams, convert to kilograms before doing any other calculation. Now, we could be asked about experiments to do with density. They haven't explicitly listed it, but we know there's going to be questions on stuff that's not explicitly listed. So to measure density, basically we need an electronic balance to get the mass, and we're going to need a ruler to work out the volume if it's a regular shape. If it's an irregular shape, we use the Eureka can. So the Eureka can, if you remember, is just basically a little metal can with a spout, and then we fill it with water. Once it's stopped having the water come out of the spout, place a measuring cylinder under, place your little object in there. However much water is displaced is the volume. Very simple. So, We are then going to think about the difference in density between the different states of matter. So if we're thinking about this in the most simple terms, go back to that chemistry knowledge about the particle model. In a solid, we have more particles in any given volume than we do in a gas. As a result of that, we've got a greater mass and therefore a greater density. So what we find there is solids will always have the greatest density, gases the lowest density. We come on to our first law at this point, the law of conservation of mass. And that just tells us that particles are neither created nor destroyed. Therefore, if we start with 1 kilogram of ice, we are going to have 1 kilogram of steam when we evaporate it. So again, they could ask you very simple questions, particularly on the foundation paper there, that if you're starting off with 1 kilogram of ice and you melt it, how much water do you get? 1 kilogram, dead easy. We then come on to looking at the difference between two words that we sometimes think are interchangeable. Temperature and heat. They are not interchangeable, first and foremost. When we think about temperature, this is how hot or cold something is. So this is what we're going to measure with a thermometer. We tend to use degrees Celsius or possibly Kelvin, but in pretty much any experiment they give you on the paper, it'll be degrees Celsius. And what this does is it gives us an idea about the average kinetic energy of the particles. If we're talking about heat, this is actually energy in the thermal store. So because it's energy, it's measured in joules, and it's going to depend on the arrangement of particles and how quickly they are moving. So what happens when we heat an object up? Well, when we heat an object, what we could see are one of three things happening, or a combination. First, we're going to change the energy stored in the system to increase the temperature. Secondly, we could see a change of state. Thirdly, it could make a chemical reaction take place. Obviously, depending on the setting, will give you an idea about what's going to happen. So it changes the energy stored in the system to increase the temperature, changes the state, chemical reactions occur. Which brings us nicely onto these two types of changes that we can see, physical and chemical changes. Again, chemistry overlap, isn't it nice on this paper? First of all, the physical change, this is a change in state. So what we see here is no new substances are made, and it's usually reversible. So what we find, this is a solid melting to a liquid, for example. Chemical changes, however, are ones that involve a chemical reaction. So as a result of this, we are going to make a new substance, and it is usually irreversible. So just remember the difference between physical and chemical changes there. We now come on to our second calculation of the night, which is all to do with specific heat capacity. Now, when we talk specific heat capacity, what we find is we're discussing the amount of energy needed to raise the temperature of 1 kilogram of material by 1 degree Kelvin. So specific heat capacity, the amount of energy needed to raise temperature of 1 kilogram of material by 1 degree Kelvin. Now, what we're going to find is that the amount of energy we need to do that is going to depend on three key things. First, the type of material we've got. Secondly, the mass of the material. And thirdly, the actual temperature rise itself. So what we actually have there is, again on our formula sheet, we've got an equation for the change in thermal energy, which is mass times specific heat capacity times the change in temperature. Key bits to look out for on this one, again, mass, probably going to be given to you in grams, so convert it to kilograms first of all by dividing by 1,000. Specific heat capacity could be given to you in a table, so you'd have to select the right material for the correct specific heat capacity there. And change in temperature. They can do things like tell you that you're going to do something along the lines of increase the temperature from room temperature to 80 degrees Celsius. They're expecting to know room temperature about 20 degrees there, okay? But remember, we're working out a change in temperature, so 80 minus 20 gives us 60. They're not going to give you different units for temperature at all. They could obviously give you the change in thermal energy and ask you to calculate specific heat capacity. So just substitute in what you know, simplify it, and then rearrange it to get your final answer. Should be absolutely fine to do that. There is an experiment that goes with this, which is this lovely little setup here. So what we can see here, we've got a little beaker sitting in some insulation in this case, thermometer one side and a little electric heater on the other. Now that electric heater is connected onto a power supply, so that what we actually are going to do is use the electric heater to heat the water, recording the temperature change. Now when we're looking at that experiment, then what we're going to find is, if we've got a material with a high specific heat capacity, then they are going to be quite resistant to changes in temperature. So it's going to take a lot of energy in order to change the temperature of that substance. An object with a low specific heat capacity is going to heat up quickly. So this is why we use certain metals in saucepans, because they've got a low specific heat capacity, they heat up very fast for cooking food. Now, as far as this experiment goes, they can ask you questions that tend to all go around the same idea. What are the potential problems and how can we fix them? So with this one, what they'll do as the most likely problems is, there will not be insulation around it first of all. So our first issue, there's no insulation, therefore heat is going to be transferred to the surroundings rather than our water or whatever liquid we've got in the beaker. How do we solve it? We insulate it. Second one is, this little heater here won't be completely covered by the water, the ice, the metal block, whatever it is. There'll be a little bit of it sticking out of the top here. So again, we can just say that not all of the heater is covered by our substance, therefore some of the energy is going to be transferred to the surroundings. How do we solve it? Make sure the heater is completely covered. So usually relatively straightforward to pick out those bits there. Because it's not being listed as one of those experiments on either the foundation or the higher tier physics, then I wouldn't think that they're going to particularly spend that long on asking you many questions on it. So we'll leave it there for now. We now come on to specific latent heat. Now, where we're talking about specific latent heat, we're going to be looking at changes of state. So this lovely little diagram here has got solids, liquids and gases. So hopefully we know the basic change of state. Solid to a liquid is melting, liquid to a gas is going to be evaporating, then as we come back down, gas to a liquid is going to be condensing, liquid to a solid is going to be freezing, and don't forget we can also go directly between solid and gas. So solid to a gas is sublimation, and a gas to a solid is depositing or deposition. So make sure you do know those key changes there. What they can do is give you this little graph, okay? So it could go either way, depending on if it's heating or cooling, but it will have a similar pattern to it. So in this case, we're heating up. So we start down here at minus 18 degrees, and we've got a block of ice at this point. So initially, we get this little hot diagonal line here, which is where the ice is warming up, because obviously the temperature is increasing. Now, what we find is we then hit this plateau, this horizontal line. And the reason that the temperature doesn't increase here is that all of the energy we're actually putting into this is going into changing it from a solid to a liquid. So rather than increasing the temperature, what we're doing is rearranging those particles from their nice fixed regular positions in a solid to the liquid. Once it's all a liquid, we then see we increase the temperature again, get to our second little plateau up here, and again that's a change of state. In this case, that's where we're boiling our water. So what we'll see here is all of the energy we're putting in is going to change in the state of the substance. Once it's all the gas, we then just increase the temperature of the gas. So just make sure you remember that any of those plateaus are where we're using the energy to break the intermolecular forces between the molecules. So the temperature doesn't change, all that's happening is we are breaking the intermolecular forces. Now, when we come to talk about specific latent heat, there are two types. We have specific latent heat of fusion, which is where the energy transferred when 1 kilogram of a substance changes from a solid state to a liquid state, or the energy transferred when we change 1 kilogram of a substance from the liquid state to the solid state. So that's fusion. whereas the specific latent heat of vaporization is the energy we transfer when 1 kilogram of a substance changes from the liquid state to the gas state, or vice versa. Again, formula sheet has us the very useful formula here. The thermal energy in joules is the mass in kilograms times the specific latent heat. What do we need to do on this one? Look out for the grams to kilograms conversion once more, and in terms of what specific latent heat value to use. What they tend to do with these calculations is they give you a little table with a range of substances, and then there'll be one column for the specific latent heat of fusion and another for the specific latent heat of vaporization. So you need to read the question and pick out what change of state is happening. If it's solid to liquid or vice versa, then it's the fusion one we use. Whereas if it's between liquids and gases, then we're going to use the vaporization column. So just make sure you pick the right substance and which one it is, okay? Solid to liquid or liquid to gas, to get the right value to then just substitute in. Of course, at this point I am going to remind you, make sure you are taking a calculator tomorrow to your physics paper. There's a whole ton of calculations on this first paper usually, and if you don't have a calculator, mental maths is all you've got to rely on, and why would you risk it? Exam situations, we make stupid mistakes. Don't do that, take a calculator. Now, we're going to come on to the next bit of P1, which is all about gas pressure. So, to start off then, if we think about a basic situation that you've all encountered before, blowing up a balloon. So, when you actually blow up a balloon, what you're doing is increasing the number of air particles inside the balloon itself. Those particles of air are going to collide with the surface of the balloon as they're moving around, and each of those collisions creates this small force. And it's those collisions that create the gas pressure against the balloon, making it push out. If we add more air particles to a container that can't expand, so think of solid cans for example, so metal cans, then what we find is the pressure is going to increase. So the more particles packed into something that obviously can't expand, we see an increase in pressure. The other aspect we need to consider is what happens when we increase the temperature of a gas. So if we increase the temperature of a gas, the particles gain kinetic energy, therefore they're going to move faster and have more frequent collisions with the side of the container. So that means we get an increase in pressure. So increasing temperature increases the pressure because they've gained kinetic energy, they're moving much more quickly, and therefore more frequent collisions with the container there. If it comes to measuring pressure, we use a pressure gauge, and that has the unit of pascals. It's unlikely they're going to go into any more detail than that, just know a pressure gauge measures pressure at that point. Now, for those of you doing GCSE physics, so either foundation or higher, you need to know this. Combined science, you can just have a little bit of a break for a moment. You need to know about pressure and volume and the link there. When we're talking about the link between pressure and volume, we describe it as inversely proportional. So what that means is that if we double the volume, then the pressure is going to halve. Be careful about phrasing here in your answers. If in the question they give you an actual kind of quantifiable value, so doubling, halving, quadrupling, whatever it may be, your answer also needs to use similar terminology. So you can't just say it increases or it decreases. That's not going to be enough. So make sure that if they say what happens to the pressure if the volume doubles, then make sure you say the pressure will halve. Don't just say it decreases. Now, when we're talking about these collisions of gas particles, the force we're creating is at right angles to the surface, okay? So make sure you remember right angles to the surface as far as our gas particles are concerned. There will be another calculation on your formula sheet here, which is the pressure times volume is the gas constant. Volume will be in meters cubed. Just double check to make sure it is. They don't tend to be overly mean on that one. If you're doing physics higher tier, this is for you. Foundation folks, combined folks, you don't need to know this. When we're considering our gases, we can actually increase the internal energy of a gas in one of two ways. we can heat it or we could do work on it. So what we do here is a good example, the good old bike pump. So when you're trying to pump up the tyre on your bike, then you've got one of those little manual pumps. And what you're going to do is apply a force to the pump, and as a result, the gas is going to get hotter. Therefore, kinetic energy increases, and that means we have more frequent collisions, because if we've got more kinetic energy, that means they're moving faster, and therefore the pressure will increase. Still just for GCSE physics, but foundation and higher tier folks, we need to know about atmospheric pressure. Now, hopefully we do know that the Earth itself is surrounded by these layers of gas called the atmosphere. Now, that's approximately 700 kilometres from the surface of the Earth towards space. And because we've got all these particles of gas above us, they push down on us. And as a result, they exert atmospheric pressure. Now, what we find is the further away from the surface of the Earth you go, then the lower the atmospheric pressure is, because there's fewer particles of gas above us pushing down. So if they ask you why it is that the higher up you go on a mountain, on a plane, whatever kind of going away from the surface of the Earth setting they give you, what happens to pressure, then atmospheric pressure decreases. Reason, there are fewer particles of air pressing down upon you. Good example of where you can see this is if you buy a bag of crisps in the airport before you get onto a plane, don't open it. Then when the plane actually goes up and takes off, watch what happens. The whole bag of crisps just expands out because those gases are then going to push out on the bag as the atmospheric pressure is decreasing, the pressure inside the bag is greater. For those of you doing higher tier physics, you need to know about liquid pressure. So what we find is any liquid will exert pressure on objects in it. So water exerts liquid pressure, etc. Now what we find is the reason for that is that those molecules within our water in this case are going to collide with each other, the container and anything else in the water, therefore creating liquid pressure. And this acts in all directions. What we find as far as pressure in terms of depth, the further down you go in water, then the greater the pressure will be. So this is why we can't take submarines or dive down to the greatest depths of our oceans, because the pressure is just too great. Second thing we need to consider is the density of the liquid. So the more dense the liquid, the greater the pressure will be. So just bear in mind that there's those two things that will affect our liquid pressure, either the depth we are or the density of the liquid itself. We do have another calculation here for those of you doing higher tier physics, again on the formula sheet, which is just looking at the pressure in a liquid. So you will see it as height of column times the density of the liquid times gravitational field strength. Now gravitational field strength on Earth is just 10, and the height of the column must be in meters. Don't be thrown if it's talking about diving in the ocean, because depth and height, same thing, okay? So whatever it is, whether it's a depth or a height, that needs to be in meters. Your gravitational field strength will be on Earth, therefore it will be 10. All you then need to do is look at the density of the liquid, multiply the lot together, and you've got your pressure. Final thing for those of you doing higher tier physics on P1 is looking at whether things float or sink. And realistically, what we're looking at here is an item is going to float if the upthrust balances the weight. Because weight is a force that acts down, upthrust acts up against it, therefore if they are equal, then what we're going to find is the item is going to float. If weight is greater than upthrust, it's going to sink. We have another calculation that could come into play here. Pressure is force divided by area. So again, on the formula sheet, you'll be able to find all of these things. So, on to P2 then. So P2 is one that we actually have listed as kind of key for both foundation and higher physics folks. So what we've actually got there, if you're doing higher tier, pretty much the entirety of P2 is listed. Foundation tier, then we've got the sort of first bit, the 2.1 and the 2.3 listed here. If they start with the most basic stuff there, then they can ask us how to measure distance and how to measure time. So quite simply, measuring distance, get a ruler. Measuring time, use a stopwatch. It is that simple. Sometimes that is a mark for each of them purely for being able to identify you use a ruler to measure a distance and a stopwatch to measure a time. Now, we can upgrade our time measurements slightly if we're looking for an improvement to an experiment there, purely by using a light gate. Now, in terms of the kind of experiments here, because we do have the speed and acceleration ones listed on the advanced info, then this is probably going to be our little trolleys and ramps kind of stuff. So again, if we're talking about looking for potential sources of error, reaction times on stopwatches is never great. Therefore, improvement, put a light gate in, because that removes the reaction time of the human being. We come on to our speed calculation. Will not surprise me if this is one of our calculation questions tomorrow in the slightest. Speed is distance divided by time. Distance in meters, time in seconds. Just look out if they're trying to make it slightly more complicated by giving you a distance in centimetres, divide by 100 to get it into metres, or a time in minutes. Obviously convert that into seconds first of all by multiplying by 60. If they're actually going to give you some other distance, I suppose they could give you kilometres. So if they've given you a distance in kilometres, then times it by 1,000. So just make sure you can convert quite comfortably in terms of centimetres, metres, kilometres, and then your time to seconds. Now, we come on to two key terms in the next bit of P2, vectors and scalars. If we're talking about a vector, then this is a quantity that's got direction and magnitude. So what we see there is this is something like a force, for example. We're going to be using arrows to actually represent our vectors then, because we can use the length to show the magnitude or the size, and then the arrow is going to show us the direction it acts in. As far as scalars go, this one has just a magnitude or a size, no direction, purely just a magnitude. In terms of common examples here then, so our vector quantity would be velocity, the scalar would be speed. Distance is scalar, displacement is a vector. So just make sure you know a couple of examples of those, because you could be asked that again as a simple question there. Now, what we come on to next is our acceleration calculation. Again, on the formula sheet, you don't have to memorise it, but it's change in velocity divided by time. Again, make sure time is in seconds first of all. When we are looking at acceleration, quite simply, it is the change in velocity per second, hence change in velocity divided by time. Now, what we find is that can be either positive or negative. If something is increasing the velocity, that's a positive acceleration. If something is decreasing in velocity, it would be a negative acceleration. So again, make sure you're using the positive and the negative signs appropriately at this point. They can ask you about acceleration due to gravity in some questions, and this is a value you just need to learn. So on Earth, acceleration due to gravity is 9.81, but they usually accept 10. 9.81 is better because it's more accurate clearly, but 10 you'll probably get away with it. Next, this is an overlap with some of your maths work. We're going on to our distance time graphs. Here is a simple distance time graph that we hopefully know. Key thing, before you do anything with any of these graphs that look like this, look at your y-axis, because what we're going to see is the y-axis is going to tell us what kind of graph we've got, whether it's going to be distance time or velocity time. So y-axis, read this first so you know what we're talking about. Now, in case of our distance time graph then, what we've got is a diagonal line first of all. So at this point, distance and time are increasing in a same proportion. Therefore, we can see that at that point we have something that is moving at a steady speed. If we have a horizontal line, then it is stationary, because time is increasing, distance is not. If we end up with a curved line, then that tells us that the object is moving at a changing speed, and if they ask you to calculate the actual speed, all you need to do is calculate the gradient of the line at that point. Now, you can obviously have a little look at things like the total distance travelled from one of our distance time graphs, because if we've got a distance time graph, obviously just read off the maximum point on there and you know how far someone has gone. If they were to give you a displacement time graph, then what you would find is it can go up as you move away, then obviously you might be stopped for a bit, and then if you return to your start point, then that line is going to be going downwards rather than carrying on going up. So obviously just look out for that from the y-axis. We then come on to our velocity time graph then. Now, because we're talking velocity, this is obviously going to have both a size and a direction. So what we've got, a few key things on our little velocity time graphs again then. So what we can see first of all is if we've got this diagonal line here, then that is a constant acceleration. Horizontal lines, constant velocity, and then if we've got a line going back down towards the bottom here, because it is a velocity graph, we've got direction, therefore it's a constant deceleration at that point. If it's curved, it's a change in acceleration. If they ask you to calculate the acceleration from one of these, all you've got to do is the gradient of the line again. The one other thing that they can ask you to calculate is either distance or displacement, depending on what kind of graph they've given you. So if they've given you a speed time graph, then you would be asked to calculate the distance. If they've given you a velocity time graph, they'd ask you to calculate displacement. But what we do is the same in both cases, because all we've got to do for that is calculate the area under the actual line itself. Now, you don't need to know any fancy kind of formulas to work out weird shapes and their areas. Literally, divide it up into two triangles and a rectangle. You know how to calculate the area of a triangle, you know how to calculate the area of a rectangle, then add them up once you've done it separately. We then come on to another one of our calculations on the formula sheet, which is all about motion. So final velocity squared minus the initial velocity squared is 2 times the acceleration times the distance. Again, it's on the formula sheet. This is more a case of just make sure you read the question and see what they've given you in terms of actual values. Obviously one of those things is going to be missing, and then whatever one is missing, substitute in all of your others, and then you can obviously solve it to a certain extent and then simplify it down. Do remember though, if it's asking you to calculate something like the final velocity, because in that formula the final velocity is squared, take the square root at the end of it. Otherwise, obviously, you've calculated final velocity squared. So just watch out for that one if it comes up. Another calculation, this is the paper of the calculations, I'm afraid. Then we have kinetic energy. So 0.5 times the mass times the speed squared. Again, on your formula sheet, you've just got to use it appropriately. Potentially rearrange it, but that's not too tricky. Now, key thing here is obviously making sure that you only square the speed, you don't square the whole thing, and make sure the mass is in kilograms. Because we're calculating kinetic energy, obviously the units for that would be joule, because all energy is in joules. Right, we are now on to the second part of P2, which is advanced info for those of you doing higher tier physics, not on the foundation, but pretty much guaranteed there's going to be at least 1 mark on it anyway. We are coming on to Newton and his laws. So we'll kick off with Newton's third law, which is for every action there is an equal and opposite reaction. And basically what that tells us is that there are these pairs of forces that are going to be in opposite directions to one another. Now, when we're considering these forces, what we find is we have contact forces and non-contact forces. Non-contact forces, as the name suggests, are ones where the objects don't need to be in contact for the force to actually act. 3 examples you need to know here: electrostatics, magnetism, gravity. Again, potential multiple choice question. It has been in the past where they literally give you those 3 and 1 other, and they're basically saying which one is not a non-contact force. Or obviously they could give you 3 random contact forces and one of these and ask you which is the non-contact force. So electrostatics, magnetism, gravity, they are the non-contact forces. The contact forces will occur when objects are in contact with each other. Name kind of tells us that. So what we see here, examples of our contact forces, we have friction, drag, the normal contact force, upthrust and tension. If we are drawing forces, which would only be those of you doing higher, then what we need to do is use the arrows. So we use force arrows for these. Contact forces we draw from the point of contact, non-contact forces you draw from the centre of the object. Now, what we will be asked to do potentially on the higher tier, and this is higher tier combined and higher tier physics, is you could be asked to draw these things called free body diagrams. Now, a free body diagram quite simply just shows the forces that act on a single object. And we don't have to draw the object. That's the nice thing. When we draw one of these free body diagrams, whatever the random object is, we're going to replace it with a dot or a box. So if they tell you that we're going to draw a free body diagram for a book, no one cares if you can draw a book in beautiful artistic recreation, because we're scientists, we don't care. We want a little dot on the page, basically. So change the book to a dot first of all. We then need to identify the non-contact pairs. So we're thinking about obviously the force of the earth on the book and the force of the book on the earth. We then think about the contact pairs. So this would be things like the force of a table on a book or the force of the book on the table. There we go. Make sure I get that one the right way around. And then what we're going to do is focus on the single object, the book. We then draw an arrow to represent our forces. So in this case, because our book is stationary on the table, we have drawn two arrows in opposite directions to each other, and they should be equal sizes. Mine may be slightly off, but use a ruler, make sure they are the same size as each other. The actual size doesn't matter, just as long as they are the same if it is a stationary object. Obviously then we just need to label that up. So make sure that you do appropriately label your forces with the arrow directions. Still higher tier folks only, whether it is combined or triple, doesn't matter, just higher tier generally. We need to know about the resultant force. So when we talk resultant force, this is the force when two or more forces are added together as vectors. Because remember, all forces are vectors, they have a direction associated. So if we've got an example where we've got 5 Newton force to the right, 5 Newton force to the left, the resultant force is 0, because obviously they cancel each other out. If we've got a 5 Newton force to the right and a 3 Newton force to the left, we have a resultant force of 2 newtons to the right. So make sure you don't just say the value, but the direction as well. Now, they could, I suppose, ask you about forces that act at different angles to each other, which is just Pythagoras. So again, the overlap with maths. This works if we've got two forces acting at 90 degrees to each other, because a squared plus b squared equals c squared, okay? So all you need to do there is obviously use the two forces they've given you, and then you can work out the unknown force. Back for everyone now, so combined and triple, higher and foundation folks, we're coming on to Newton's first law. When we talk about Newton's first law then, this just tells us that an object will continue to stay at rest or continue to move with a uniform velocity unless a force acts on it. So in order to actually change the speed or direction of that object, we need that resultant force. For higher tier folks, we need to know that if the resultant force is 0, then the speed or direction of the object will not change. And this is all linked into the ideas of inertia. And quite simply, inertia is the measure of how difficult it is to change an object's velocity. So this comes down to the real basic principle that moving objects are going to keep moving, stationary objects just stay stationary. Everyone again now, we need to understand that if we've got an object that is not moving, okay, then the resultant force is 0. Therefore, we have something at equilibrium. So when we're looking at equilibrium, that just tells us that the forces are cancelling out. The resultant force is 0. So just watch out for that phrase coming in every once in a while here. We're now going to come on to Newton's second law. That is all to do with the acceleration that the resultant force produces on the object. So it tells us that the acceleration the resultant force produces on an object is to do with the size of that resultant force and the mass of the object itself. So what we will find here is we're basically using one of our formulas from the formula sheet. Force is mass times acceleration. Again, make sure the mass is in kilograms, and then you should be able to use that absolutely fine in any calculation they give you. They can bring in some of these experiments on this, and because we do have speed and acceleration experiments listed, there's a potential for this one. So again, it's going back to our little trolleys, but this time what we've got is a little string attached to the end of the trolley with masses on the end across a little pulley system. So the idea being that when you actually release the masses, then it's going to make the trolley accelerate. There's a couple of things to bear in mind on this particular experiment. Firstly, we need to make sure that the ramp has been compensated for friction, because between the wheels and the surface we will have friction. So in order to do that, we just raise the ramp ever so slightly until the trolley is going to move at a steady speed. Secondly, if we're timing with a stopwatch, then we can improve it by using a light gate to record the time, because that removes the problems with our reaction times there. The next thing we need to consider is basically motion in a circle. So when we actually have things that move in a circle at a constant speed, it is still accelerating. So any object moving in a circle is accelerating. Not because the speed is changing, but because the direction is changing. And remember, when we talk about acceleration, that could either be a change in speed or a change in direction. So objects going in that circular motion will be accelerating. We then come on to the idea of terminal velocity. Now, the way that they phrase this will be different scenarios depending on the given year of the paper. It's usually skydivers or people diving off a diving board. Now, one thing I am going to say is there was one year, quite a while ago now, where there was a really quite mean question asking about what forces are acting on the skydiver in the picture. Now, everyone leapt straight in by saying weight and air resistance, because as people are falling through the air, of course they're the two forces that are interacting. They didn't look at the picture to see that actually the skydiver was standing on the ground. Therefore, look at the picture, because what we have, weight, absolutely, that will still be acting in that downwards direction, but acting up would have been just that normal contact force. Look out for them being just particularly mean. It doesn't come up frequently, but every once in a while they could be cruel. So spot that one in the picture just in case. Don't just assume. Now, if we think about the situation of someone jumping off something high up, okay, we're going to use our skydiver in this case. So that as you jump out of the plane, then what happens is you have a force exerted on you by the earth, and that is going to be greater than the force the air is exerting against you. So as a result of that, force going down is greater than the force going up, therefore you are accelerating down towards the earth itself. What we then find is, as you accelerate down, what we're going to find is that the force of the air resistance is going to increase. What we then find is eventually we get to a point where those two forces are going to equal each other. So we're going to end up in that equilibrium situation. And at that point, where those two forces are equal, then we are going to continue falling at a steady speed, which is our terminal velocity. Obviously, if you kept falling at that terminal velocity, having just leapt out of a plane and did nothing about it, it wouldn't end well at the other end because there would just be a pull. So we need to open a parachute. Now, opening a parachute means that we've got a giant bit of fabric, basically, that is then going to have a much greater force of the air resistance, because there's more particles colliding with the fabric of the parachute, therefore air resistance increases. As a result of that, air resistance is greater than your weight, and therefore you're going to start to slow down. As you then slow down, we find that the air resistance decreases, and therefore we eventually reach this new lower terminal velocity. And we can see it in these two little versions of diagrams to help us understand it. So here we are, we leap out of the plane and we're initially accelerating because weight is greater than the air resistance. Because we accelerate, air resistance increases, therefore we start to slow down. At this point, we have got those forces in balance, therefore terminal velocity. Open the parachute, we decelerate because we then see the situation where our air resistance is greater than the weight, and then we reach our new terminal velocity at a lower speed that allows us to fall safely onto the ground without turning into a puddle of mush. For those of you doing higher tier, if they're being particularly mean, they can ask you about forces at angles. Now, if we're dealing with forces that act at different angles to one another, you'd have to resolve them, because you can only use forces that act in two directions at right angles with each other. In terms of how you do that, I don't think they're going to get you to do it on the exam paper, so we're not going to spend time today. We are just going to go on, if you want to look at that, you can on the channel, but we're not going to spend time on that one tonight. The next bit is for everyone, so combined and triple higher and foundation folks. So what we actually find then is, if we're thinking about everyday examples of where forces take place, one of the key ones they like to talk about is rockets trying to take off from the ground. So what we actually find is the resultant force from all that fuel burning in the rocket produces a large acceleration, enough to basically let the rocket accelerate off and lift off from planet Earth itself. The reason is, as we burn the fuel, we're going to be pushing gases out of the bottom of that rocket. Those gases are going to push on the rocket pushes on the gas, so we have Newton's third law there, every action has an equal and opposite reaction. And when we actually get to the point where the force of the gas on the rocket is greater than the force of the Earth on the rocket, then it's going to accelerate and lift off. If you're doing higher tier, then we need to know about momentum. Now, momentum depends on two key things, mass and velocity of an object. Again, on the formula sheet, you are going to find the formula for this. So momentum is mass times velocity. Now, what we find is the mass must be in kilograms and velocity meters per second. They're not going to get you to convert that one. Again, just look out for the grams in the question and make sure that you convert it before substituting in. Still just higher tier folks on our momentum. If we have any form of collision, in theory momentum is conserved. That's our law of conservation of momentum. So that's going to tell us that the momentum before has to equal the momentum afterwards. So this could be a case of they're giving you a little diagram telling you the momentum beforehand and asking what the momentum after would be. It would be the same, okay, if that's a simple question. What we're going to see is that we could see two types of collision here, elastic and inelastic collisions. Elastic ones are where kinetic energy is conserved. So if we're talking about one thing coming in and hitting the other, then what we find is the kinetic store must have the same amount of energy before and after. So in that situation, if we've got an object coming in and hitting another, coming to a complete stop, then this ball or object is going to move off at exactly the same velocity that that one came in at, because we're not losing any kinetic energy. It's all literally being transferred from one object to the next. The reality is different. So what we actually find is that when we're looking at what happens if two objects do collide, then not all of it is going to end up in the kinetic of the new one. Instead, some of the energy is going to be transferred to the thermal store by sound, for example. That is our inelastic collision then. So inelastic collisions are ones where the kinetic energy is not conserved, therefore some energy is transferred to other stores, okay? So just think about it. Anything that generates a sound or anything like this in the form of a collision, then it's inelastic because some of that energy is transferred to the thermal store as that sound then. Back for everyone, so this is combined and the triple, the foundation and the higher tier folks. We have another calculation which is work done. Work, quite simply, is the transfer of energy. So in order to calculate work done, it's just force times distance. Again, distance must be in meters. So use your formula sheet to use that one. That can sometimes be paired up with a second calculation about power, which quite simply is the rate of transfer of energy. Again, on your formula sheet, you're going to find the power is work done divided by time. They could do a two-part question here. So first part, getting to calculate work done. Second part, calculate power. They could make it a bit trickier and just ask you to calculate the power, but they'll give you time, force and distance. So they're not going to explicitly tell you to calculate work done, but you certainly can't just jump straight to calculating power without calculating work done first. So obviously look at what they give you in the question. And if you're looking and thinking, well, you've asked me to calculate power, but I don't have what I need to do that, look at the formulas, and it'll be the same section of the formula sheet in this P2 section. What do you have? It's almost like a ticking exercise. Look for the thing you've got 2 bits of, you can then calculate that third. And then obviously you can use that to calculate your power. The next bit of P2 was all about what happens when we apply forces to different objects. So first thing we need to understand is that we've got 2 types of material, plastic and elastic. If we're talking about a plastic material, this is one that's not going to return to its original shape once the force is removed, whereas an elastic one will return to the original shape once the force is removed. And this brings us very nicely onto one of those pads they've listed, good old Hooke's law. So you should in theory have done this experiment where you had a clamp stand, a little spring stuck on the end, you added masses and then measured the length of the little spring as it extended. You would have then plotted the graph something like this. Now, key things as far as Hooke's law experiments go. First of all, in terms of potential sources of inaccuracy, the fact that the spring might still be bouncing slightly when you measure it. So obviously, improvement, make sure that the spring is not moving before taking the measurement. Make sure your ruler is completely vertical, because if it's at a slight angle, you're going to get an inaccurate measurement there. And obviously, just make sure that when you are doing this, you are measuring the extension on it. Wouldn't surprise me if this was a graph drawing question, so they could very well give you a set of data and ask you to plot this particular graph here, because they can then ask you to explain what it shows as well. Obviously, I have not seen the paper, so I can't guarantee that, but there's going to be a graph somewhere for drawing. Now, key things with our graphs when we come to drawing a graph on an exam paper. First of all, make sure you use a pencil. There is only that one little bit of printed graph paper in your exam paper. That's it. There's no spares. So if you mess it up in pen, then you've blown it basically, because drawing it just randomly on the additional lines and things, you're not getting all the marks anyway because it won't be accurate. So what you've got to do is use a pencil first of all. You need to pick an appropriate scale, and the bit of graph paper will have been selected in size to make it so there's an obvious scale that's a decent size. You need to use half the horizontal and half the vertical space. Don't use less than that. Don't draw this piddly little graph in the corner. More than half vertical, more than half horizontal, you will get that mark then for the size. When we then put our axes on there, make sure you label them with units. So what you tend to find is that having those axes labels with units can be a mark on its own. When it comes to plotting the points, please can you actually use a nice clear little cross. Don't just do a tiny little dot that then gets hidden by the line when we draw it. Make sure you do a little cross so that we can still see it when any lines are drawn. Then obviously if we're talking lines of best fit, do look at the data properly. Okay, so most graphs you will either have a straight line or a curve, so just pick the appropriate line of best fit. In this case, what we have is a straight line to start, and then we've got this curved end here. So what we can see on this is initially, as we increase the weight, then the extension increases. They are proportional to each other, because for every 0.5 Newton increase in weight, we are getting, it looks like about a 2.4 increase in extension. So we get that very regular pattern there. we will have that right the way up to this point here where it starts the curve, which is the limit of proportionality. Now, beyond that point, what we find is that the spring is going to be permanently deformed. So make sure that you can label the limit of proportionality on the graph. Make sure you understand that if we go beyond it, then the spring will be permanently deformed. There is a calculation here again on your formula sheet, which is the force exerted by a spring is the spring constant times the extension in meters. Again, look out for that centimeters in the question and convert to meters first of all. If they ask you to calculate the spring constant from the graph, quite simply, all we need to do is calculate the gradient of this linear section here. So again, just draw your little triangle under your graph, work out difference here, difference there, and then just divide to get the gradient. They can ask you to calculate the energy transferred in stretching. Again, it's on the formula sheet. 0.5 times the spring constant times the extension in meters squared. Again, go careful not to square the whole thing. Make sure that you are only squaring the extension. Make sure the extension is in meters, and then obviously just substitute in. Formulas on the formula sheet, you don't have to memorize it. Now, what we find is that whereas for our spring we had that nice linear section initially, if we were to do the same experiment with an elastic band, we do not have a linear relationship. So what we get is more of a wavy line going on there. So obviously that would be a difference between those two graphs that we would see. We're now going to come on to the idea of gravitational fields. So when we talk about a gravitational field, this quite simply is a region where mass experiences an attractive force. So the gravitational field strength is going to be a measure of the force that acts on 1 kilogram of mass when it's in a gravitational field due to another mass. One thing to remember, mass and weight are not interchangeable again. So mass is basically the amount of stuff something is made from, measured in kilograms, whereas weight is going to be the force measured in newtons. Now, what we find is that the force that acts on an object within a gravitational field will be larger if the mass of the object is larger or the distance between them is smaller. So the closer the objects are and the greater the mass, then the greater the gravitational field is going to have that force. Now, our gravity force quite simply is mass times gravitational field strength. And remember, on Earth, that is just 10. So mass in kilograms times gravitational field strength gives you gravity force. Again, that's on your formula sheet. Just remember to use it. When we then come to consider our whole idea of gravitational potential energy, when we lift up something within a gravitational field, we are transferring energy to the gravity store. And this is referred to as gravitational potential energy, or GPE. If you want to just write GPE on an exam paper, that's absolutely fine. You will still get the marks. You don't have to write gravitational potential energy. GPE, absolutely spot on. And the GPE of an object depends on its mass and its height. Formula sheet will have this lovely calculation for us. GPE is the mass in kilograms times the height in meters times gravitational field strength. So again, two conversions to look out for there, kilograms and the meters. Now, only for those of you doing the GCSE physics combined, folks, you don't need to know this bit at all. Then we need to understand a few different scenarios where we use these forces. So first of all, we can have our turning forces. The point around which those forces act to produce a turning effect is a pivot, and the moment is the turning effect of the force itself. Those moments are either going to be clockwise or anti-clockwise. So if in doubt and it's giving you a question on moments and ask you what direction it acts in, pick one, clockwise or anti-clockwise. Even if you don't know, 50% chance of guessing it right. Again, we've got a calculation on the formula sheet. The moment of a force is the force times the distance. Distance in meters once more. Now, we then come on to the whole idea of using some simple machines, and the most simple machine we can use is a lever, which basically is something like a rod that's not going to bend with a pivot, so that when we apply a force at one end, we produce a force in the opposite direction at the other end, and this is a force multiplier. A relatively small force on one end creates a much larger force on the other. So this is why you can do things like open lids of cans of paint with a screwdriver, for example. What we find is you could be asked to calculate mechanical advantage, which is just the load divided by the effort. More likely is that they're going to talk to you about gears. So gears are made of individual little cogs, and what we need to know is the ratio of the diameters of the cogs, because the ratio of the diameter of the cogs will tell you the ratio of the effort and the load. So if we've got a cog with twice the diameter of the other one, we will multiply the force by 2, okay? However, that larger cog will only move half the distance of the smaller one, because if it's twice the diameter, then one rotation of the smaller cog is only going to create half a rotation of the larger one. So they have asked questions on this in the past in terms of how much the force is multiplied and the distance it moves. So just think logically, okay? You should be able to just apply those basic kind of principles of, if this one is twice the diameter, then we're multiplying the force by 2, but it's only going half the distance. So just apply that same principle, whatever they've given you there. There is another calculation to pressure at this point before we go on to our hydraulics ideas, still just for physics folks, which is the force normal to the surface divided by the area of the surface gives us the pressure there. So basically what we see here is we get a greater pressure with a greater force, or if we increase the area of the surface, we increase the force. Now that's the basic principle, if you like, of how hydraulic machines work. Now a hydraulic machine is going to use a liquid to transmit a force from one place to another. And one of the best examples of this is things like the hydraulic lifts that we use for cars. So when we want to lift a car up in the garage, it uses a hydraulic lift. So what we find then is that between the actual device that we're pushing down one side and the car going up, there's going to be a fluid within that area. Now what we find is, because we're going to be going to a much larger area, then we're going to have a larger force. That's why our relatively small force on one side allows us to lift the car on the other. And that is the end of P2. So on to P3. This is back for everyone combined, and the physics, foundation and higher tier folks. We're going to start off with the idea of electrostatics. So nice little recap first of all with overlap on chemistry. Protons have a positive charge, electrons have a negative charge. You should hopefully know the different relative charges and relative masses of those subatomic particles. So proton +1 and a mass of 1, neutron 0 and a mass of 1, electrons -1 and a relative mass of 0.0005 or 1/2000. Do remember that atoms are going to be neutral overall because they have the same number of protons as electrons. In terms of producing an electrostatic force, what we actually do is we get two insulators, and that's a key word to remember here, two insulators that we're going to rub together. At that point, electrons will be transferred from one substance to the other. So one is going to have more electrons, therefore it becomes negatively charged. The other will have less electrons than protons, therefore it is positively charged. Please be careful, remember only the electrons are moving. Now, they can give you this little question about why water bends when you hold the little static rod next to it. And there all you need to do is go back to the basics of the rod has a charge, the water has, and depending on which way it's bending, either the same or opposite charge, and then you explain it in terms of opposite charges attract, like charges repel. So it really is as simple as, if the water is bending towards the rod, then you can say the rod has a positive charge, the water has a negative charge, so they are being attracted because opposite charges attract. Whereas if the water is bending away from it, then you could say that they both have the same charge and like charges repel. If we connect our object to a piece of metal, then those charges are able to flow, and as a result the object becomes discharged. It's also worth bearing in mind that we can discharge objects through the production of a spark, and obviously a spark is dangerous if we have flammable gases present. For those of you doing GCSE physics, we need to know this next bit. Combined, you don't. When we're talking about electric fields, these are being produced around charged objects or charged particles. So we end up with this kind of setup here. So we can see that we've got positive and negatives, and if we've got positive and a negative, we are going to have these field lines between them. They're going to connect because they're opposite, therefore they attract. Do notice how the arrow goes from positive to negative. If we've got two of the same charges, so like charges, then obviously the lines are not going to be connecting between the two, but still make sure the arrows always face away from the positive there. What we find is that if we place another charged object in an electric field that already exists, field lines are going to stretch. Now, what we're going to then find is a force is going to act on the object in the same direction that would cause those field lines to shorten and straighten. The only other bit that they could really ask you with regards to these diagrams is they could give you a series of diagrams with different numbers of field lines. If we've got large numbers of field lines close together, then we have a stronger field. Right, back for everyone then, so combined and triple, higher and foundation, we are coming on to the idea of our circuits bit. To start us off, we need to know that current is the rate of flow of charged particles, or the electrons. In order to make current flow, we are going to need some kind of a power supply, a cell, a battery, etc., and the circuit must be complete. And if we're talking about a series circuit, so a single closed loop, the current anywhere in that loop will be the same. We come on to our first calculation of P3 here, which is charge flow is current times time. Again, on the formula sheet, just make sure you use it and make sure the time is in seconds. One thing to watch out for on this is if they're throwing in milli things. So milliamps could come in here, for example. Now, if we're talking milliamps, then basically 1 milliamp is the same as 1,000th of an amp. Okay, so 1 milliamp is the equivalent of 1 times 10 to the minus 3 amps. Our next bit is just learning our circuit symbols, and I'm not printing them out. So you just need to know your circuit symbols, folks, because they could ask you to draw a diagram for a particular setting. So make sure you know those common ones, the cell, the lamp, the switch, etc., the ammeter, the voltmeter, the different types of resistors. So make sure you know those because they could ask you to draw a circuit diagram in the exam paper. Now, what we find is that for current to flow in a circuit, we need potential difference. And in order to generate that potential difference, we have a separation of charges inside our cell or our battery. So one side is positive, the other side is negatively charged. There is a potential difference between the two, therefore current will flow once it's connected into our circuit. Do remember when we are drawing these different terminals, the positive and the negative, on our circuit diagram, then the positive terminal has the longer line. The negative terminal is the shorter line. And do make sure that they're quite explicit when you're drawing them. Don't draw it so it looks very similar. Make it really clear for people. Now, another calculation, energy transferred is potential difference times charge. Again, on the formula sheet, just make sure that you use it. I don't think they're going to have any conversions in this one. Should just be a nice straightforward calculation should it occur. We now need to understand the difference between series and parallel circuits. So in a series circuit, then the current is the same everywhere. So wherever we place our ammeter in that series circuit, we will get the same reading. If we are placing a voltmeter into a circuit, then we need to make sure that we are connecting it in parallel. So when it comes to an ammeter, that one always goes in series. So you can see it's actually in the main loop. If we were asked to connect our voltmeter in to work out potential difference across the bulb, you've got to put it in parallel there. So please be careful with that because people often make that mistake. And sometimes they even give you questions where they've drawn a circuit diagram with the ammeter and the voltmeter in the wrong places. So you find the voltmeter in series and the ammeter in parallel. So look out for those, and you can obviously suggest the improvements there. When we're looking at our voltmeters, then what we are able to do with those is measure the potential difference across a component. So what we actually find is that when we're actually connecting our voltmeter, if we do that to all of the components in our series circuit, then they will add up to the same potential difference across the battery. If we think parallel circuits now, then the current in all of the loops adds up to the current near the battery. So if we placed our ammeter somewhere near the battery, then that will have one reading, and if we add up the readings on the ammeters in all of those separate loops of our parallel circuit, they will equal the same. Now, potential difference across each component is the same as the potential difference across the battery in a parallel circuit. So we've got some clear rules to remember here. They could ask us some troubleshooting problems in terms of building circuits in a practical setting. So generally speaking, think about what we can do. If the bulb doesn't light up, check the battery works first of all. If that then does work, check the bulb. If that still works, then what you want to do is check each lead in turn, swapping out one lead for another in turn, okay? So just think about how you can problem solve if that comes up. Now, our next calculation is a very important one, and I would almost place money on this being on the paper tomorrow for at least some marks, which is V equals IR. Okay, so potential difference is current times resistance. Now, the current is actually dependent upon the potential difference and the resistance in the circuit. It is a dependent variable. The only way we can change the current is by changing either potential difference or the resistance in our circuit. And we have this whole thing called Ohm's law here, which just tells us that the current is proportional to the potential difference if the temperature does not change. So V equals IR on the formula sheet, you're going to use it at some point tomorrow. Please do. It's usually a lovely, easy question. Now, on to our next little bit about resistance. When we're thinking about resistance, this is bringing in the idea of the structure of a metal. So our metal has got positive metal ions and delocalized electrons, remember. So these delocalized electrons have got a negative charge. They've obviously been knocked out of the actual structure of our metal atom to make it a metal ion, positive and delocalized electrons. These delocalized electrons are free to move through the structure of the metal. Now, what we actually find is that when those electrons collide with the metal ions, we produce resistance. And for those of you doing higher tier physics, they've listed this PAG, the resistance of a wire PAG there. So what we actually need to do is think about the factors that could affect resistance. First of all, a thinner wire has greater resistance than a thicker wire because there's more chance of the electrons colliding. Same if we've got a longer wire. The longer the wire is, the greater the resistance will be because there's more chance of the electrons colliding with those positive metal ions. In terms of the resistance of a wire practical, this was the one where you had a meter rule and you had a bit of resistance wire probably stuck onto it. You then use your crocodile clips, one at obviously 0, and then you connect it at say 10 centimeters, write down your readings. Move it along to 20 centimeters, record your readings and so on. Because what you'd have in your circuit would be an ammeter and a voltmeter. If we've got potential difference and we've got current, we can then calculate resistance. So you just do that in turn, moving it along the wire as you go. Safety features, the wire can get hot, so obviously not touching it, making sure you're not leaving it switched on for large amounts of time on the power pack, etc. And if they ask you how you can improve any of your results, look for things like they're only doing it every 10 centimeters, so do smaller intervals, every 5 centimeters, for example. Now, we come on to the idea of types of resistor now. We have fixed resistors, which have one resistance, and it is that resistance only. And we have variable resistors. Now, variable resistors allow us to change the amount of resistance wire the current is flowing through. So think about dimmer switches here. That's the example where you probably used one. When you twist your little dimmer switch, what you're really doing is you're moving the amount of wire that your current is going to have to flow through in order to complete that circuit. For the foundation physics folks, your PAG was all about circuit elements. So this could be our characteristic graphs bit. When we're talking characteristic graphs, this is where we've got current plotted against potential difference. So in order to get these values, we've got to measure the current flowing through of a given component at different potential differences. And we need to do both positive and negative values to do this. So remember that you've got to reverse the connection on your battery or power supply and repeat the whole thing to get the negative values as well as your positive ones. We can find linear circuit elements, so these are the ones that have a resistance that does not change. So this is our linear circuit element here, nice simple diagonal line passing through our origins at 0, 0. Now an example of that would be a fixed resistor or resistance wire, for example. We then have non-linear circuit elements. These are the ones where the resistance does change. That's things like your lamp. So that's this little graph here. So we can see that we've got this curvy line that the resistance is changing at that point. Now the reason for that is that as those electrons are colliding with the metal ions in the wire of our lamp, those ions vibrate more. That means the wire gets hotter, and that's going to then affect the resistance. Our next little characteristic graph we need to know about is the diode. So that's this one up in the top corner here. Now diodes are dead easy to spot because what you'll see is there's going to be a steep increase on one side of the graph and a complete flat line on the other. Because the key thing about a diode is that it only allows current to flow in one direction. So you will only find changes on either the positive or the negative, but not the other side. Now, thermistor is our next one, which is a resistor that changes its resistance with temperature. The reason it does this is that it's made of a semiconducting material called silicon. So that what happens there is that because it's a semiconductor, the silicon is able to lose electrons from its structure relatively easily. Now, what that means is that as we've got our thermistor in our circuit, then when it becomes heated, the electrons are going to gain enough energy to escape the atoms, and therefore the resistance is going to drop. So the higher the temperature, the lower the resistance will be. And you'll see that on our little graph here. So we can see increasing the temperature is going to be decreasing the resistance. We get a similar setup with our light-dependent resistor, the LDR, but this time it's going to be based on the light intensity. So what we see in terms of our light-dependent resistor is increasing the light level is going to decrease the resistance there. Now we come on to the whole idea of net resistance next. So when we're talking net resistance, that is basically the resistance of a circuit if we took out all of the individual components and replaced them with a single resistor. The net resistance in our circuit will change if we swapped components for different ones, or if we change the arrangement of those components. If we think about the most likely scenario for this, we're talking about adding an identical lamp. So if we were to add an identical lamp to our series circuit, current decreases and the net resistance increases. If we were to do the same thing but with a parallel circuit, then the current increases and the net resistance decreases. So just make sure you remember the difference between them and read the question to see whether it's series or parallel. Now, they do have a habit of asking you questions regarding series and parallel circuits where you're going to be calculating something like the resistance of a component. Now, in order to do this, basically we need three key things. 2 facts and the formula from the formula sheet. Thinking about series circuit first of all. Fact number 1, current is the same everywhere. So whatever current they have told you anywhere in the circuit, that will be the same for the entire circuit. Fact number 2, the potential differences across each component add up to the potential difference across the battery. So normally what they'll have done is given you a potential difference across the battery, they will tell you the current somewhere in the circuit, and they will give you the resistance of something. So from that, we can then work out the resistance of the other thing in the circuit using V equals IR. Because if we know the resistance of that one component, then we already know the current, because it's the same everywhere. We can then obviously use current times resistance to get the potential difference across that first component. We then have got the potential difference across our battery minus the potential difference of that one component we know. That then gives us potential difference. The current is the same everywhere. We can rearrange and calculate resistance. For the parallel circuit, similar thing, but the different facts. Fact number 1, potential difference is the same across each loop. Fact number 2, the current in each loop adds up to the current near the battery. Formula, V equals IR again. Same sort of principles of doing that calculation. Even if you can't get to the end, look at it and think, okay, what can I calculate? Basically, use V equals IR for something, and you've got some of the marks on that question. What we find is that in terms of our circuits, we can set up these things called sensing circuits, which are using things like light-dependent resistors or variable resistors, pressure sensors, etc. So if they're going to ask you a question about that, just think about what the setting is and therefore what kind of resistor is most appropriate. Final thing in P3 is our power. So power, remember, we've already talked about one of the ways that we can calculate it, but there's a range of different power calculations you're going to find on the formula sheet. So you will have power is potential difference times current, you've got energy transferred is power times time, and power is current squared times resistance. Depending on what they give you in the question, just pick the right one to use and you'll be absolutely fine. Right, here we go, P4, the final bit of the whole of our first paper. So this is the magnets bit. If you're doing combined science, it's the end of P3 still. For those of you doing triple, it's called P4. So for everyone, we need to know that if we have two bar magnets and we place them together, like poles repel, opposite poles attract. The most basic bit about our magnets there. Now, do remember, if you're drawing any field lines on magnets, then the arrows need to go from north to south. The number of the field lines that we see on a diagram representing that magnetic flux, then that tells us the strength. So more of those lines, it's a stronger field. We have two types of magnet. Permanent magnets, these are ones which are magnetic even when other magnets or the current is removed. And an induced magnet is one where it will only be magnetic when it's in a magnetic field. The way we explain that is through something we refer to as the domain theory. So the domain theory is basically saying that within our little magnetic material, so something like iron for example, we have these small regions called domains that are not lined up. When we place them into a magnetic field, those domains all line up and therefore it generates its own magnetic field. When we take it back out of the magnetic field, the domains return to their original directions and it loses its magnetism. Our next little bit is looking at how we actually generate a field around a wire. So if we have a current flowing through a single piece of wire, then there is a magnetic field around it. And the magnetic field in that case is going to be a series of concentric circles. So literally, if they ask you to draw the shape of the field around a current carrying wire, it is this, circles inside each other. Now, we do need to add the direction, so the actual arrow to show the direction on there, that's one mark. Second mark is going to be for your arrows. And this is where we're going to use our right hand, okay? It's the old thumbs up. So what you're doing is your thumb is going to point in the direction the current is flowing in, and then the way your fingers curl is going to tell you the direction the arrow goes in. So literally just sit there with your thumb, put it, if it goes up, then you can put your arrows going that way around. Okay, so literally right hand, thumbs up, and your finger curl shows you the direction it goes. Now, what we actually can do as an experiment to show that a wire produces a magnetic field when that current flows is you connect the wire into your circuit and you're going to place a compass next to the wire. When we then obviously turn that on, what we see is the compass is going to align to that field. So you would have done experiments here with a little plotting compass, moving it kind of top to tail around and then just marking each point there. In terms of that field strength, our magnetic flux strength or magnetic flux density will depend on two things: the magnitude of the current and the distance from the wire. So basically a bigger current leads to a stronger magnetic strength, and the closer it is to the wire, the stronger our magnetic strength will be. If we have a loop of wire, then what we're going to find is we still get our concentric circles on each side where it passes through our cardboard, but down the very centre it's a straight line. So just remember that little point just in case it comes through. We can also use a device called a solenoid. Now a solenoid quite simply is a coil of wire, and if we've got lots of loops we will have a stronger field, so this is why we use a solenoid. If we wanted to make that even stronger, what we do is inside that coil we just put a magnetic material in the centre. So that means that when the current flows through, that magnetic material is going to become magnetic and it just makes it a stronger magnet overall. For those of you doing higher tier, you need to know what happens when we actually place a current carrying wire inside another magnetic field. And the answer is they're going to interact. So what we see is those two magnetic fields are going to push on each other and create a force on the wire. And that force is always going to be at right angles to the magnetic field. This is where Fleming's left-hand rule comes into place. So first thing to get right is use your left hand. And then what we're going to do is use this lovely arrangement here. What we have: thumb, first finger, second finger. Your thumb is going to be the direction of movement. Your first finger is going to point from north, where your palm is, to south, where your fingertip is. And your second finger here is going to be pointing in the direction of your current, positive to negative. So what we're going to see here is you are going to have, almost certainly, a situation where they will give you a little diagram, something like this, and they will ask you what direction is the wire going to move in. So it's Fleming's left-hand rule to do this, so you'd have to get your hand facing north to south, and you'd have to look at the direction of your current. Now, if you really can't work it out and you're just sitting there flipping your hand in different directions and just getting a bit stressed about what the answer is, then you can just go with simply up or down. Because in all likelihood, the way they're going to draw that diagram, I can't think of another example where it's gone a different direction, just up or down will be an answer for you there. Still just higher tier, folks, there is a calculation that comes in here, which is the force on a conductor carrying a current, there we go, is magnetic flux density times current times length. Again, check that length is in meters, not in centimeters again. Other than that, current and your magnetic flux density should just be given to you as standard. So, just higher tier, folks, we need to know about motors. This is where we've got a loop of wire and we've stuck it in a magnetic field. So because it's a loop of wire, then what we're going to find is, on the two sides of the loop, then our current is flowing in opposite directions. So we can see here it's going that way on this side and this way on that side. As a result, think Fleming's left-hand rule, then this side is going to move down and that side moves up. Because obviously our current is going in the opposite directions in that same magnetic field, one side goes up, the other side goes down. Therefore, the whole thing is going to turn. In order to allow that coil to spin continuously, then what we need to make sure is that we don't see it changing directions. So in order to achieve that, we use this little device down here called a split ring commutator. Notice how there is a little gap in the ring itself. So what's going to happen is, as it turns, obviously it's going to disconnect and then reconnect, so that what we find is that this side, okay, whatever is on this side of the setup, is always going to be moved in the upwards direction. Now, 4 key ways that we can actually change the speed of our motor. First, we can increase the actual magnitude of the current. Second, we can increase the strength of the magnetic field. Thirdly, increase the number of coils in the wire. Or finally, increase the length of the coil. So 4 ways that we can obviously change the speed of our motor there. Magnitude of the current, strength of the magnetic field, number of coils, length of the coil. For those of you doing physics higher tier only, you need to know this. It's electromagnetic induction. If we move a wire in a magnetic field, what we're going to be doing is cutting field lines. Now, as soon as we cut field lines, then we are going to create this induced potential difference across the wire. Now, what we actually find is that by actually cutting those field lines, we've got that induced potential difference. Now, we don't just have to move the wire to do that. We could also do it by changing the magnetic field. So there's a couple of ways that we can do this. But the key principle is the field lines must be cut. If no field lines are cut, no induced potential difference is produced. 3 ways that we can increase our induced potential difference. We can move the wire faster, use a stronger magnetic field, or use more wire. All of them work on the same principle, that more field lines will be cut in that same time frame. So, what we find, if we connect the wire to a circuit, then we are going to have a current flowing. Because when our current flows in a conductor, a magnetic field is produced. What we then find is that wire, if we place it into a magnetic field, is going to have a force acting on it. Because remember, we've got, obviously, our current in our conductor, that's generating its own magnetic field. Place it in another magnetic field, we are going to have a force acting on it. That force is going to be in the opposite direction to the original. So what we see here is a good example is the old magnet dropping down a pipe. So the magnet as it falls is going to induce a current in the pipe. That means that we're going to then produce this current in our pipe, because it's a closed circuit. That produces its own magnetic field. The direction of the current opposed the change in the magnetic field, therefore it repels the magnet and it falls slower through the tube than it would do if it was a plastic tube. Still higher tier physics, we are on to generators now. We're going to have a little look at 2 different things at this point. We're going to look at generators and alternators. If we think about an alternator, first of all, we've got a coil of wire spinning between the poles of a magnet. So as a result, we're going to generate an alternating potential difference because our potential difference is changing direction. What we find here is we are going to connect this whole thing onto these things called slip rings. Now notice those slip rings are resting against an item called a carbon brush. They're not physically attached, they literally just rest against the side of it. So that means that we're always connected in the circuit, but it's not as physically attached. Therefore it's not going to just twist up and create a tangle. Now what we actually find then is in this one, because it is an alternator, we get an alternating potential difference. So that means positive to negative and so on. In terms of our dynamo then, this one is going to create a direct current, or DC. The reason for that is the potential difference that drives our current will not be changing direction. And in order to achieve that, we use a split ring commutator, just like we had in our motor there. Now, in terms of our alternators and our dynamos, there are 3 things that we can do to increase the output. We can use a stronger magnetic field, more turns on the coil, or we can spin the coil faster. So any of those works there. Still just for higher tier physics, we need to know about transformers next. Not robots, but purely something we use, and this will come up in our second physics paper as well. Transformers are a device that we are going to use to either increase or decrease the potential difference. Now, as we've already said, potential difference is induced when magnetic field lines cutting coil change. Therefore, we can change the field lines cutting a coil in one of 3 ways. We can move the magnet or the coil, we could use another coil, turning the current in on or off, or we could use a coil with an alternating current. All 3 of those are going to have the end result of inducing potential difference because the magnetic field lines cutting the coil will be changing. Now, what we have in terms of our transformer then is this. We've got two coils around this iron core. So we have our primary coil and our secondary coil. The number of little turns in each of those coils is going to tell us what type of transformer we have. The way it works then is our transformer has got this loop of iron. So basically that iron core, when we generate a magnetic field, is going to trap the magnetic field within it. So an alternating potential difference across our primary coil is going to produce that alternating current in the primary coil, and that produces our magnetic field in the iron core. Because it's an alternating current, that magnetic field is constantly changing. As a result, our secondary coil on the other side will have a potential difference induced in it, because the field lines there are constantly changing. Two types of transformers we have, step up and step down. A step up transformer is the one that increases potential difference, and you will always be able to identify it because it has more turns on the secondary coil compared to the primary. Step down transformers decrease potential difference, more turns on the primary compared to the secondary. Our last little section then is literally the loudspeakers and the microphones. Physics folks only, but higher and foundation. So combined folks, nothing to do for you here at all. So, microphones first of all. The most common type of microphone is the dynamic microphone, which behaves kind of like a generator. So what we actually have here then is our dynamic microphone setup. We've got a magnet, we've got a coil of wire that sits over it, and that sits against the diaphragm. Now, our sound wave is a pressure wave, so that as the sound wave hits the diaphragm here, it's basically going to make it move in or out, depending on, obviously, whether we've got higher or lower pressure. As the coil moves in or out, it moves over the magnet, and as a result, we're going to induce a potential difference across it. So basically, as the pressure wave hits the diaphragm, moves the coil over the magnet, cuts the field lines, we induce a potential difference across the ends of the wire. That's the electrical signal from our microphone. They're unlikely to ask you about a carbon microphone, but we'll quickly recap it anyway. So carbon microphones just have carbon granules behind the diaphragm. As that sound wave hits the diaphragm, it changes the resistance of the carbon, and therefore a current passing through those carbon granules changes because of that change in resistance. Final thing is our loudspeaker, which basically behaves like a motor. Now, in this case, what we're going to do is we've got our coil of wire over a magnet again, and this time what we're going to see is, as that changing potential difference produces changing current, that's going to produce a force on the coil of wire because it's sitting in a magnetic field. And remember, if we've got a current, we've got a magnetic field, two magnetic fields together interact and therefore create a force. As a result of that, it makes the actual cone of our loudspeaker move in or out, and as it does so, it creates a sound wave because it's going to create areas of high pressure and areas of low pressure. And that is it. That is all of our physics work for our first physics paper. Hopefully you managed to get that through my voice going a bit weird and wacky in the middle, and I wish you all the best for tomorrow. Key things to do with the physics paper: number 1, use the formula sheet. Number 2, take a calculator and use it. Number 3, look out for those conversions. So look out for their centimetres, not metres. Look out for the grams, not kilograms. Make sure you do the conversion first of all. So anything else, just read the questions carefully. We know obviously a chunk of the paper because OCR are staying pretty true to their advanced information, which is good, but we also know there will be some questions on the other bits. Nice thing is, a chunk of this one is calculations, so show you're working nice and clearly, and then you should be able to get a really good grade on it. So all the best for tomorrow, and hopefully see you again for our next live stream for, it'll be biology paper 2. So night before biology paper 2, we'll be back to do all of that. Have a good evening everyone. Remember to get some sleep as well before your exam.